Okay, so today we will look at some solver settings and turbulence models. This today is going to be a theoretical session, so no workbench needed. So I will start the PPT. Okay, so solvers and turbulence models. Firstly, let's look at the types of solvers that we have in Ansys. So if you would have noticed in our previous simulation, there are basically two solvers in the general window it appears. Here you can see in this dialog box, there are two types of solver, pressure-based and density-based. So let's look at the comparison. And here I won't be discussing any transport equations or basically any equations that are involved. I will only be talking about the applicability. Okay. So firstly, pressure-based. So pressure-based model was generally used for incompressible flows, meaning when the density is not changing. And density-based solvers are used for compressible flows. Okay. So subsonic flow, yes, the pressure-based solvers are only used when the flow is subsonic in nature. Okay, but basically when the speed of the flow is low. And density-based, for high-speed flows and even for supersonic flows, we prefer density-based. And okay, I would like to clear here that it does not mean that we cannot solve any compressible flow problem with pressure-based, or and we cannot solve incompressible flow problem with density-based. We can do we can do it with either of the solvers, but it may give us some convergence issues. It will produce divergence. I'm speaking this with experience. So yeah. And nextly, yeah, the shock waves. So generally, whenever we are dealing with any supersonic problems, we are always concerned with the shock wave resolutions. So in pressure based, yeah, we cannot resolve any shock waves easily. So if the flow is supersonic, then you should always go for density based. Okay. And yes, that's why, because in density based there is a shock resolution. So even if there are any normal shocks or oblique shocks or even expansion and compression waves, you can easily solve it with density-based solvers. And yes, so generally the pressure-based solver gives faster convergence. But you know, since we cannot solve compressible flows with no, not we cannot solve supersonic flows with the pressure base. It does not matter if it is a faster convergence or not. And yes, so even if we are trying to solve incompressible flow with the density-based solver, the convergence will be a lot slower. So that's why for incompressible flows, pressure-based is used explicitly. So this was just a general comparison. So if you want to select the solvers, and then you will select on the basis of the problem that you have. So if you are expecting any shock waves in your domain, then choose density based. And if your flow is very high speed, then also go for density based. And if your flow is very relatively simple and incompressible flow, then you can opt for pressure based. Okay. So next, we will, yeah, let's look at the methods that are involved in the pressure-based solver. So when you go to the methods tab on your left side of the solver setup, there are always a scheme in each of the solvers. So there are four schemes in the pressure-based solver. Uh, Two of them are segregated algorithms, which is simple and simple C. If you scroll down in this scheme dialog here, there will be four methods basically, which you'll be able to select. So out of these, simple and simple C use segregated algorithms, and this piezo and coupled methods use coupled algorithms. Okay, so what are these algorithms? So okay, so generally that you know that all of the governing equations that are involved while whenever we are solving any type of equation, they are always coupled equation. Okay, so in this segregated algorithms, we segregate or we separate these equations and then we solve them separately. Okay, so that's why that's why the name comes from segregated algorithms. We are basically decomposing all those equations that are naturally coupled equations and making the problem easy. And in coupled algorithms, there is no decomposing here. The algorithms are solved as it is meant, and so governing equations are solved simultaneously. And yes, the segregated algorithms, like I said, they are very simple and they are very memory efficient, but they often gives us slower convergence because you know that equations are solved separately, and then reaching the final solution will take time. So if let's say with segregated algorithms, you are reaching the convergence by say 20 iterations, and you will find that in coupled algorithms uh, this convergence is faster. So if you use the coupled algorithms for that 20 iterations that you took in our simple algorithm, it may take only 10 or 15 iterations. So coupled algorithms always have faster convergence, but consecutively it needs more memory to solve. Okay, so it's usually you have to decide based on your problem and based on your computer specifications that which solver that you will be using. So generally, you can find that in most of our problems we will be only using coupled algorithm because I know that we are only concerned with the faster convergence. So nextly, yeah, there are density-based solver. Then even in density-based solver, there are two schemes: explicit scheme and implicit scheme. So for what it is, this explicit is similar to that segregated algorithms, but not exactly because it is solving for all the variables at only one cell at a time. Okay, so for yeah, yeah. So for each cells, there will be some equations uh, which will be independent of the equations at neighboring cells. Okay, and that's how it will solve these equations. And in implicit scheme, it will solve for all the variables in all cells at the same time, meaning that firstly it will form all those equations for the cells and then it will solve it. And like in the explicit scheme, firstly it will solve for as soon as it is making the equation for the cell, it will solve them as well. Okay, and just like the segregated algorithms, explicit scheme is memory efficient, but the convergence is slower. And you can guess in implicit scheme, this convergence is faster, but it needs more memory. Next, yeah. So, like I said, in previously in the pressure-based and density-based, we can like pressure is mainly used for incompressible and density is for compressible flows. But that does not mean that we cannot solve compressible equations with pressure-based because this compressibility or incompressibility is defined in this materials tab. Okay, not in not by choosing the solver. So in the materials window here, you can see on the right hand side, we can decide if the flow is incompressible or not by setting this density formulation. This first option is for density, and by default it's constant. That means the density is constant. That means the flow is incompressible. So in the density method, you can choose constant for incompressible flows and ideal gas for compressible flows. So if you, there are many other options other than these two, but mainly we are concerned with these two only. So and also there is like other user-defined methods, like you can give your own formula for density, okay, based on other variables, but generally you won't be using it unless you are some pro coder in CFD. And nextly, we'll see the viscosity. So viscosity method. Usually we keep it at constant. We keep it at constant when there are no viscous effects. Okay, that means when the let's say when there simply when there will be no viscous effects, when like the flow is very turbulent. Okay, then there won't be any viscous effect. But if the flow is laminar, there will be viscous effects. And this, let me tell you, experimentally, it has been found that this viscosity of the any fluid is dependent on the temperature. Okay, so what you can do is to to simulate the reality of the flow. you can set it to Sutherland method. Sutherland basically making the viscosity temperature dependent. And definitely, if you are setting it at Sutherland, these viscosity effects will not be ignored, and it will be shown in the calculation. Okay, its effects will be produced in the calculations that you do. And yes, so before we move on to the turbulence model, we must discuss about this y plus value. And y plus value is such an vast topic that this for just to cover this topic, I may need an extra class. But for today's session, I will keep it very short. So secondly, y plus value is used for turbulence models only. Okay, so in laminar flow, you won't be needing this y plus value. Only in turbulent flow, like wherever we are concerned with the boundary layer. So what is this y plus value? It is the non-dimensionalized distance of the first cell from the wall. Okay, I will tell you what that means. You can see that in any turbulent flow, you will see that there are boundary layer that is formed. Okay, this happens like in every turbulent flow, and as much as it is reacting with the wall. Okay, so we are concerned with the first cell. So suppose this is the whole boundary layer of the flow, and above this black line is the free stream. So if you have made a mesh in such a way that your first cell is above this boundary layer, okay. So here you can see that this is the first cell in this example, but let's say your first cell is at here, okay, like this is the first cell, okay. Then you will find that these boundary layers are not resolved properly. Okay, but which means that yeah, these variations in the boundary, these won't be visible in your contours and other results. Okay, so and this will also disturb the flow, the free stream flow as well. Okay, because since this is not resolved properly, and this will like just like a chain reaction, the other solution will not be accurate as well. Okay, the region which is not near the wall. And if you have made a grid in such a way that it is refined near the wall, like in this example, here you can see that first cell is lying, and not first cells, like 10 cells are lying in the boundary layer almost. So what this does is then we will be able to resolve this boundary. Like if there is some velocity, like at this point the velocity will be different, and at this point the velocity will be different. So similarly, we will be able to resolve this boundary layer, and this boundary layer is in meshing is what we call the inflation layer. Okay, I will tell you in this next class that we will be doing for our wedge analysis. Okay, and I will make this like y plus inflation layer at the wedge. Okay, and nextly, yeah, so for resolving this boundary layer, y plus value should be between 1 and 30. Okay, for 1 and 30, it means that first cell will probably lie in this layer. So which means that even these like sub layers, even the viscous sub layers will be resolved. So I will be giving you some of the references regarding this y plus value. You are free to check it out. Actually, it is a very vast topic for me to cover in one class. So okay, so yeah, this y plus value is what we will like models. Different turbulence models are related on this y plus values because some models this high resolution is not needed because there are already some corrections which are already implemented. Okay, so yeah, we will check out the turbulence model now. There we will discuss it. So RANS turbulence models. RANS means Reynolds average Navier-Stokes turbulence model. So like you know that Navier-Stokes is not a closed equation. It is an open equation. That means there are more number of variables than number of equations. So what we have to do is we basically have to introduce some equations to that Navier-Stokes equation to close that equation. And while we are introducing those equations, we also have to model them to just close the problem. Okay. So first model is Spalart-Allmaras. This is SA model. This is a very popular model for the analysis of airfoils. Okay, here, yeah. So wherever model I'm writing no wall functions, that means you need a very fine grid near the walls. That means you have to make your grid very fine near the walls using the inflation layers or any method actually. So yeah, the advantages are firstly there are low memory requirements. You won't like memory will be saved because it is only a one equation model. Like you are solving the Navier-Stokes by introducing only one equation. Okay, so that's why it is less complicated. And yes, this is a very stable model. That means convergence. Yeah, it will be very. It will show good convergence, and the flow will be stable in your domain if you choose this model. Okay, and it is, yeah, even if you haven't resolved mesh as much, it won't it will be less sensitive to that chain reaction that I talked about previously. Like if even if the values near the wall are not correct, it won't affect the solution which is far away from the wall. Okay, but still you will need like a great refinement near the wall. And yes, the only disadvantage is it is very inaccurate for free flow, shear flows. And as soon as the like flow is separating, like there are different velocities at each point in the flow, and that is what a shear flow is. And for those type of flows, this is a very inaccurate model, and basically for decaying turbulence. And let's say the airfoil analysis. Suppose in 0 degree, you know that uh, this boundary separation occurs like at very end of the tailing, like at the very end of the airfoil, at the tailing edge of the airfoil. Okay, so in that case, Spalart-Allmaras will be good. But let's say you increase this angle of attack, and now what will happen is this separation will occur very quickly. So to simulate this separation, this model is not very accurate. Okay, so for that separation, we will be using some other models like we'll see. So next model is K-epsilon model. Yeah, this is also very popular model. So for free shear flows, shear layer flows, I mean. So with a very small pressure gradients, like a very small pressure changes. Okay, this flow is very good. This model is very good. And yes, there are wall functions which is implemented. That means if that near the wall, you can keep the y plus value between 30 and 100. And if you keep that value, then you'll find that you need less number of elements in your domain. And yes, consecutively, if you are keeping your y plus value to be like between 1 and 30, you will find that number of elements will be needed will be much higher. Okay, we will see that in our practical example as well. Okay, so yeah, so wall functions are implemented. And yes, here also there are low memory requirements. Now this standard K-epsilon is a two equation model. Okay, this K-epsilon and K omega are always two equation models, and that means two equations will be introduced. And this also shows good convergence. There is like much less instability compared to other higher equation models that we will see. And this is also like this is very inaccurate for adverse pressure gradients. Like I said, this will be only be good for when the pressure gradients are very small. That means pressure changes are very small in the flow. Okay, if there are like some absurd number of absurd pressure gradients, this model is not very good. And also, suppose you have too many curvatures in the geometry. Okay, that could be a problem for the standard K epsilon to solve. And there are other variations of K epsilon which we will use, and that are good in these cases. And also the jet flow. So you know that this plume after the jet that is made. Okay, so to resolve that plume, this model is not very good. Okay, there are other models that we'll see for that purpose. Yeah, so RNG K-epsilon, this is another variation of the K-epsilon. This RNG means renormalization group. Okay, you don't need to concern about that acronym for now. So it is generally more accurate and reliable than standard K-epsilon, and it is specially made for the rotating flows. Okay, like if there are some rotation is there, mainly like eddy flow like that, then RNG K-epsilon is very good. Okay, and secondly, yes, this model is very favorable for your internal flow simulation. Like we talked about the flow in pipe. So if there is a turbulent flow in pipe, then this RNG Epsilon model is very good. Okay, and yes, if this vortex, the yeah. So you know what is vortex shedding?
No, sir.
Okay, so basically, let's say your airplane is flying and suddenly a gust of wind comes. Okay, then that is basically what vortex shedding is. Like that will generate some eddies, some unfavorable eddies, and that's why vortex shedding will happen. And if this vortex is evolving with time, generally in airplane this does not happen, but sometimes what happens is, let's say, if the flow is very turbulent, let's consider an example of airfoil. If the flow is very turbulent, then those eddies behind the airfoil will also be evolving. Okay, then in that case, you may find that it may give some inaccurate results, but not that much. And for steady state solution, yeah, for steady state solution, this is not a very good model. If this, you will prefer this model in only transient simulations. Okay, and yes, this will take some 10 to 15% more CPU time than your standard K epsilon model. And nextly, yeah, this is the third variation of the K epsilon model. This is the realizable K epsilon model. Now, whatever the disadvantage that we had in previous two models, you won't be having it in this model. So this is again better for rotation flows and flows where wherever there are strong pressure gradients, it is also good for that. And even in the uh, recirculation, oh, even in the recirculation zones that are formed, this model is very good. And even in the mixing, like if you are using some multi-phase simulation, you are trying to simulate the mixing of two elements, you can say two fluids. This model is good. And basically the channel and boundary layer flows. Channel is like pipe flow, like a bounded flow, you can say. And this model will predict that spreading like outside the jets very well. Okay, like I explained, whatever the plume after the jet that you get in real time, this will be able to resolve that plume and other things. Okay, so yeah, so one thing that okay, I will discuss this later. So let's come to the standard K omega model. So standard Q omega model, again, there are no wall functions. That means you have to make that grid very refined near the wall. And again, since this is also a two equation model, there will be no low memory requirements. And yes, this generally it is often used where K epsilon models fail. That means near the walls. Okay, so K-epsilon models, like we have seen, it is very good for free shear flows. Okay, which means when the flow is, somewhat away from the wall. For that region, the K-epsilon model is best. Okay, but for the near the wall region, this K omega, you will find that K omega model produces much more accurate results near the wall. Okay, and this is yeah, very, again, it is very inaccurate for adverse pressure gradients, strong curvature and jet flow. And nextly, yeah, this is also very oversensitive to inlet turbulence properties. So what we can do at the inlet is we can define like how much turbulent the flow is. Okay, and if that definition is not actually correct, let's say, this won't give like the expected results. Okay, so let's say if you are doing some analysis, like you are comparing your results with some experimental analysis which is done in wind tunnel. So in wind tunnel, the turbulence is very less. So, okay, we have to change the parameter. We will see this when we will come to the solver setup of the K omega, like how you can manipulate the turbulence properties. And nextly, yes, again, it is very sensitive to initial guess. So you have to be careful while using this model. And nextly, the SST omega. Yeah, the SST, if you are a beginner in Ansys and you don't know, like you are confused between all the models, you can just close your eyes and click on the SST omega model. SST stands for shear stress transport. This is like the most popular model. So, like I said before, that K epsilon model is used to calculate the flow region far from the walls accurately, and this K omega model can calculate the flow near the walls accurately. This SST K omega is the combination of both. That means what it does is when the region is near the wall, it will solve it with K omega model, and as soon as the region moves away from the wall, then it will switch to that K epsilon model. That's why it is arguably the like best two equation model that you can ask for. And yes, the only problem with this is it may converge slowly than other models. And yeah, the one of the problem, I won't say it is a major problem, but it is a problem that it can sometimes overestimate the turbulence in regions like after the airfoil. So you may get like there are too much eddy formation, like more than the experimental results. So that's what the overestimation in the turbulence means. And nextly, this Reynolds stress model. Okay, so if you don't know that what should be the expected result of your flow, okay, only then you will choose this model because it is very good for solving generally any question generally, but this convergence will happen very slowly and it will consume much more of your CPU time than you would want. Like it will take some 15 to 20% time more than K epsilon and some other like generally for laminar flow problem it will take like 50 to 60% more of your CPU time. Okay, so that's why it is very computationally expensive model, this Reynolds stress, because yeah, let me tell you, this is a five equation model. So in Spalart-Allmaras, we used only one equation, and K epsilon and K omega, we used two equations. In RSM, we use five equations. So you can just imagine like how much complicated you have made up your problem to solve. So yes, so this is the end of my PPT right now. These are all I have covered, like all the popular models that you will use. There are some other models like LES and DES, detached ready simulation and large ready simulation. Those models are used in generally 3D analysis, and we will discuss them later when we will actually come to our solver setup, when we use them and when we not. So this just covers our session for today. And Krisha, if you have any doubts, you can ask me right now.
So we have to choose our model on the base of our problem.
Yes.
So in problem they have mentioned that these are the conditions. So by looking that we have to choose the models and solvers.
Yes, yes. So only by looking at generally, yes, by only by looking at some boundary conditions, you can figure out what models you'll be using. Basically, you can figure out the pressure-based and density-based model, but for turbulence models, yes, you need some previous experience. And yes, like I said, if you are like confused about it, just close your eyes and click on K omega SST, and that's the model that we'll be using like in most of our simulations coming. So yes, anything else?
Okay. No, sir.
Okay, okay. Okay, then I will stop the meeting.